All right. Hi, everyone. Thanks so much for coming. Today, we're very happy to have Temple visit us from Caltech, telling us about from the infrared triangle to finite causal diamonds. Temple got his PhD at Harvard, working with Andy Strominger, then did postdoctoral research at UC Davis, and he's been at in Caltech for 3 years?
My fourth year.
Fourth year, 4 years. Yes, please.
Okay. Thank you, Nima, for the introduction and also for the invitation to come here. This is actually my first time in Indiana, so it's quite nice. Okay, so I'm going to talk about some work that I've been doing in the last couple of years. And actually, this all stems from some work I did when I was a graduate student, which focuses on what is called the infrared triangle. So over the last decade, we have come to learn that there's an amazing equivalence in the infrared sector of both gauge theories and gravity. And this is called the infrared triangle of equivalence. And so you can see, so the equivalence is the three corners of the triangle. So each corner designates a field in theoretical physics that has been studied for over half a century now. And they've been studied separately by different communities. So the memory effect, for instance, was first studied by astrophysicists, asymptotic symmetries by general relativists, and soft theorems by particle physicists. And the size of the triangle is essentially what we have learned in 2014, which that these three corners are actually describing the same physics phenomenon, just using very different language. So for instance, we can think of the soft theorem as the Fourier transform of the memory effect. We can think of the memory effect as corresponding to vacuum transitions between two spontaneously broken vacua associated to the asymptotic symmetry. And similarly, we can think about the soft theorem as a word identity associated to this asymptotic symmetry. Now, one of the consequences of this, of course, is that in order to have vacuum transitions, you need to have multiple vacuum state. Now, in first year QFT, at least I learned that there's a unique vacuum, and this is how you can define S matrices. We now learn that there's, in fact, that is simply not a true statement. There are, in fact, infinitely many vacua, each of which is, you can think of it as being labeled by a cloud of zero energy gravitons or soft gravitons, or if you're in the context of gauge theories, they are photons or gluons. You can think of these clouds of soft gravitons as essentially a fingerprint for which vacuum state you're sitting in. And so oftentimes, we also call these objects soft dressing. Now, how is this related to the memory effect? So the memory effect, let me first explain how it is classically understood. So suppose you have two celestial objects like stars or black holes, and they are separated from each other by some fixed spatial separation. Now you pass some gravitational waves or gravitational radiation between the two objects, and you would expect their separation to fluctuate when the gravitational wave is passing through. And after the wave has passed, you would expect their separation to be fixed once more. However, their separation before the gravitational waves passing and after the gravitational waves passing is actually different. And it's that difference that is a signature of space-time recording the existence of this gravitational wave passing through at some point. And that's why it's called the memory effect. Please.
Sorry, very naive question. Is this like some breaking of some symmetry, the vacuum?
Yeah, so it's the spontaneously, so these vacua correspond to the spontaneously broken asymptotic symmetry.
And that's a global symmetry?
Good. So it depends on what you mean by global symmetry. So part of this, all of this is disentangling the terminology that we use. By asymptotic symmetry, what I will use it's a symmetry that acts non-trivially on asymptotic states, full stop. So global symmetries that you're probably familiar with are asymptotic symmetries. But asymptotic symmetries, they can also depend on the space-time parameter. So sometimes, for instance, you can think of asymptotic symmetries as gauge symmetries that change the asymptotic data in a non-trivial manners. And I know it's confusing because we're trained to think of gauge symmetries as being redundancies. But if you look at the details of what we mean by gauge symmetries that we learned in class, those gauge symmetries, they always die off at asymptotic infinity. So those are indeed as gauge redundancies. The large gauge, so we sometimes also call asymptotic symmetries, large gauge symmetries, because these are symmetry transformations that do not die off at infinity and they act non-trivially on the physical states. Yes, and please interrupt me at any point.
So would you say that from the point of view of purely boundary correlators, this is a global symmetry?
This is allowing for if you allow for the symmetry transformations to potentially have non-trivial space-time dependence. Or are you assuming when you say global symmetry, do you just mean a symmetry?
Global symmetry, from the point of view of purely boundary correlators.
Boundary correlators.
So operators on the boundary.
Okay, what do you mean by global symmetry? Can you?
Something that well, I mean the zero form symmetry. But anyway,
Okay.
Let's talk about it.
Sure. I think the answer to your question is yes.
Yeah.
Okay. And it turns out that this memory effect that sort of captures this offset in the separation between the two objects, it can be interpreted as a vacuum transition between two different vacuum. That's what I said previously. Why are we interested in the memory effect? Well, there's an experimental reason for why. The gravitational memory effect, once we detect it, it will be a non-trivial check of general relativity. And it is believed that, in fact, advanced LIGO already have enough data to verify it. When I talk to experimentalists, they seem optimistic that if you accumulate multiple signals, you can actually increase the signal to noise ratio, and you can see the imprint of the gravitational memory effect in their data. But even if we do not see it at advanced LIGO, there is another experiment that is hopefully will be launched soon that can detect the memory effect. And this is the LISA experiment, where you have, it's a space-based telescope. You have 3 laser interferometers. They're shooting lasers between these two detectors. And so if there's fluctuations in the separation between any of the two detectors, it will manifest itself as a phase shift.
Yeah, can I ask a silly question?
Yeah.
So, of course, this is way outside of my the realm of what I know, but like, so I'm under the naive impression that when the gravity waves goes through LIGO, these rods, they oscillate, and that's what we observe.
That's right.
So how would a signal for memory effect look like?
So that's why, in fact, you're pinning exactly the reason why it's so hard to detect gravitational memory effect with LIGO is because if the pendulums, if there's an offset, it'll just swing back, right? So you have to look at the higher harmonics. Like, because if there's an offset at the very beginning, then the swinging pattern will be different than if it's just oscillating around with no offset.
But do you need more than 2 perpendicular rods, or can that data recoverable from that?
I'm not okay. That part I'm not sure. Yeah,
Thank you.
yeah. So, yeah, the short answer is I'm not sure. Yeah. But in any case, LISA is something that is very it's sort of essentially you can think of it as it's almost built to because it will detect this offset in separation before and after a gravitational wave passing between the 3 detectors. Yes.
Okay, so what I'm trying to understand is that due to the propagation of this radiation wave, you're having the memory effect in the first place. So am I trying to correlate it with something like it is corresponding to some asymptotic symmetry spontaneously broken? If yes, so in that case, what is the symmetry group that we're trying to identify?
Right. So the symmetry group associated to the standard gravitational memory effect is for our space is the super translation symmetries. That's the leading large gauge symmetry group associated to an asymptotic fast spacetimes.
Only super translation, not rotation.
Super rotations have it's called spin memory. So there is another memory effect. It essentially is this offsetting angular momentum after a gravitational radiation pass through, but it's much smaller and it's not expected to be detected by certainly not by LIGO. I'm not. It's subleading to the leading gravitational memory effect.
Yeah, just a follow-up question to that. Since we know that memory effect, you can have 2 sorts of polarizations. One can be plus and cross. So if your super translation is one of the symmetry groups, why not super rotation?
No, there is a memory effect associated with super rotation. Yeah, it's just that it's subleading to the super translation memory effect. Okay, so traditionally, when people talk about the memory effect, it's always there's a classical source that's creating a gravitational radiation that's sourcing the memory effect. But it turns out that you can actually have quantum fluctuations that can also source the gravitational memory effect. So this was the motivation in studying shock waves in this paper that I wrote with Anna Maria Raclero and Catherine Zurich. This pair of papers in 23 and 24. Essentially, you can think of these quantum fluctuations as corresponding to shock waves, but these are not shock waves that are sourced by some sort of classical source. There's no like stress energy tensor turned on here. But this is purely shock waves that correspond to the graviton fluctuations themselves. And it turns out that these shock waves, without turning on any classical stress energy tensor, they also source a memory effect. And so one way that you can think about these quantum source memory effect is in terms of spontaneous vacuum transitions between the different vacua. So it is a natural question to ask, what is the size of these quote unquote quantum memory effect?
Can you provide a little bit more physics intuition? So this is to be viewed as a, say, pair creation of gravitons? How am I supposed to think of?
Right, so you can think of this as, it's a little bit tricky to think about these, roughly speaking, it's a little bit difficult to talk about these in terms of gravitons because when you say gravitons, I tend to think about Feynman diagrams. But Feynman diagrams presuppose the existence of a single unique vacuum. So I will talk about this in a bit. I think one thing that we would love to understand is how to think about this in terms of graviton exchanges. At the moment, I don't know how to think about everything I'm going to tell you about in terms of graviton exchanges. So just to be fully transparent. The way that I think about this is there are local energy fluctuations that are captured by, which I'll talk about, captured by the bonding mass aspect. So this is asymptotic data that characterizes local energy fluctuations. And changes in the bonding mass aspect, what it does is it allows for, you can think of it as creating soft gravitons. And soft gravitons change you from one vacuum to a different vacuum. And so it's in that sense that we're thinking about essentially that was by studying the shock waves, we're essentially capturing this sort of vacuum transition that's going on, even in the presence of no stress energy tensor whatsoever. It's basically, instead of turning on stress energy tensor, what you can do is you turn on the bonding mass aspect. And the bonding mass aspect, it's in fully vacuum spacetime. There's absolutely no matter anywhere, but nevertheless, you still see these sort of shockwave behavior.
They're L-Planck suppressed, right?
Well, it depends. They are indeed L-Planck suppressed, yes. The question is, what power of L-Planck?
Right.
Yeah. Okay. Okay, but there is, so what is the size of these quantum memory? In fact, there's another way of asking that. It's just like, what is the size of length fluctuations due to quantum effects at leading order? And if you take a look at standard EFT methods for computing the size of this, this is something that has been known for decades. So it is 10 to the minus 35 meters. This is also more recently, the calculations, this is certainly not an exhaustive list, but it was also more recently carried out the calculation by Carney, Karidas, and Shivaramakrishnan, as well as by Friedel Oberfrank. And this is 20 orders of magnitude smaller than the size of a proton. And so if this is indeed the size of these length fluctuations due to quantum effects, we just don't have any experiments to see it within our lifetimes. On the other hand, it is also important to keep in mind that this calculation was done assuming that there is a single unique Lorentz invariant vacuum. So there is a starting assumption here that is simply incorrect. And so what we hope in this part of this program is to try to understand what is a proper calculation of the quantum memory effect without restricting ourselves to the standard EFT methods, where we have an assumption of a single vacuum. And there is some, excuse me, there is some stake that we have in this game. It's that there's actually an experiment that is being built at Caltech to look for these sort of possible fluctuations. It's called GQuest, and it's a 5-meter laser interferometer, and it's built in collaboration with Fermilab. And the point of this experiment is to look for metric fluctuations on the order of 10 to the minus 17 to the 10 to the minus 18 meters. And this is at the megahertz frequency. So the hope is that we will be able to get to a point where we can give the experimentalists a clear prediction on what we expect the size of the quantum memory effect is. It could very well be in agreement with the standard EFT calculation, but at the very least, we should do a calculation that starts with proper assumptions in the first place.
There's 10 to minus 17, 10 to minus 18. That's like electric scale almost.
Possibly.
Yeah, it's about that scale.
Okay.
Yeah. Just
Yeah.
Uh-huh.
Okay. Okay. So today we're not going to be able to answer that full question, what is the size of quantum memory effect, but we are going to take steps towards understanding how to think about quantum metric fluctuations from a first principle standpoint. And what we're going to do is we're going to focus our study on the study of finite causal diamonds. The way that we're going to study these finite causal diamonds, though, is that we're going to utilize the refined understanding we have of asymptotically flat gravity. So our calculations will apply to cases where the causal diamond is very large, but still finite. And in particular, we're going to focus, roughly speaking, on 3 papers. So the first one, it focuses on constructing the causal diamond phase space. The second one, it allows us to connect the phase space of the causal diamond to the vacuum asymptotically flat gravity. And finally, we're going to construct a vacuum state of a large causal diamond utilizing this correspondence. So let me be a little bit more precise in what I want to show you. So the first part, we're going to explore the finite causal diamond phase space, and we're going to connect it to the asymptotically flat gravity phase space. And in particular, we're going to, after we do that, we're going to be able to show the relationship where the variance of area fluctuations of this finite causal diamond is proportional to not just the UV scale, but a product of the UV scale and the IR scale. So A is the area and G is Newton's constant. And the way that we're going to do this is by constructing the vacuum density matrix associated with a large causal diamond explicitly.
Right. Do you have in mind that the causal diamond is defined in a different variant ways by shooting some null of white rays? Is that how you're imagining this?
So I have something much more simple-minded. So we are working really with just semi-classical gravity. So the way that you can define it is indeed probably what you're saying, which is you shoot light rays forward and backwards, and this carves a domain of dependence associated to one sphere. What we're going to do is a more lowbrow way, where essentially we just define a region in Minkowski spacetime. We think of this as sort of our background metric in the laboratory. For example, everything is only perturbative in what we're doing. Yeah, that's right. Okay, so any more questions? Okay, so if not, let me just continue. So what do I mean by finite causal diamond? So first of all, I want to explain why we want to do an asymptotic analysis to study this. The reason why we want to do asymptotic analysis is because asymptotically things are just simpler. Oftentimes we can ignore interactions because there are fall-off conditions for the interacting fields that die off at infinity. But of course, we also oftentimes, when we're doing actual experiments, we don't want to study the entire spacetime. We actually care about finite causal diamonds. Now they're macroscopic, so we can think of them to be large causal diamonds. So what we're going to try to do is we're going to try to utilize a lot of the simplification that happen in an asymptotic analysis and apply it to finite causal diamonds. That's kind of the intuition behind this. And in particular, what we're going to, as a first pass, we're just going to look at a very simple toy model, which is we're going to look at what are the degrees of freedom that's governing a spherically symmetric causal diamond, where its area is allowed to fluctuate. And of course, since it's spherically symmetric, when I say area fluctuation, I really mean it's just radial fluctuation. So this is just an S wave mode in these causal diamonds. So here I just drew a spacetime diagram of the causal diamond. So here it's just a spherical region, a radius L, and H plus and H minus just corresponds to the past and future horizons. So this is just delineating the domain of dependence of the sphere of radius L. And here I have labeled the degrees of freedom that turns out that captures fully these spherically symmetric fluctuations. So A is the area of the causal diamond, and mu you can roughly think of it as being the time derivative of the area. So if you have like a quantum mechanics example in mind, where we have position and momentum being the degrees of freedom. Position, you can think of it as being A, and momentum, which is like the time derivative of the position. That's roughly speaking. And just wanted to point out one more thing. Notice that both degrees of freedom, they're actually not on a codimension 1 slice, but they're actually on a codimension 2 slice. So they're living just at the corner. So sometimes people also call these edge modes.
Sorry, can you say again the derivative thing? So it's A and what is the derivative?
Mu, I'll show you exactly what mu is, and then yeah. Okay. So going back to Nima's question about like how do we define the region? So this is our very lowbrow method of defining the region. So let's just start with a spherically symmetric causal diamond in Minkowski spacetime. This is just a Minkowski metric. And now let's just simply define a region as follows. So this is just carving out a subregion of Minkowski spacetime where the radius is maximum at r is equal to L. It is very convenient for us to translate this subregion into, or rather this metric, into Gaussian null coordinates. And so you can perform a coordinate map, and you can translate this Minkowski region into Gaussian null coordinates as follows. So now the future horizon is delineated by r tilde is equal to 0. U tilde is a clock along the future horizon, and phi is a dilaton that's controlling the size of the transverse sphere. So I just want to draw your attention to notice that phi is maximum at L, and this is a way of seeing that we are really describing just the region inside the space-time diagram that I drew on the previous slide. And kappa here is essentially the surface gravity. So now you can use covariant phase space formalism to determine what is the symplectic form. And at the end of the day, the symplectic form, after all the dust have settled, we get a symplectic form that is completely localized at the corner, which we also call the bifurcate horizon. This is where the path and future light rays where they meet. So A here, this is just the area because phi at the bifurcate horizon, this is just L to the D. And so the omega D is just a unit, the area of the unit D sphere. So this is just literally the area of the spherical region that you're considering. And e to the mu, to answer Nima, your question, this is why I mean that it is roughly speaking like just the time derivative of the area, because phi is related to the area, it's the radius. And so this is how you see the mu, the dependence between the area between the time derivative area and mu. It's not exactly the time derivative area.
Sorry, what is U tilde?
U tilde is a time along, you can think of it as Rindler time along the null hypersurface, roughly speaking.
Oh, you had the U, right? So U tilde and
U tilde and U are related, but they're not the same. Yeah, there's an exponential factor that's associated.
This is a very standard thing we do. It's just Gaussian null coordinates, degrees of freedom, and their corresponding derivative in the null direction.
That's right.
That's the standard.
That's right. Yes, just thing. Yeah. Now it is useful to think about A and mu because A is like the area and mu is related to the time derivative of the area. But actually mu diverges because mu is actually related to kappa U tilde minus plus alpha, where U tilde minus is minus infinity because that's where the corner is located in U tilde coordinates. So you might be worried that this causes symplectic form to diverge. But it turns out actually that as long as the surface gravity is just dependent on the size of the causal diamond, which seems a reasonable assumption, that piece completely vanishes when you take the symplectic form due to the antisymmetry of the wedge product. And so as a result, your symplectic form, you can write it as actually the symplectic partners being A and alpha, where alpha is like offset in the null time in Gaussian null coordinates. I will use the symplectic pair between A and mu and A and alpha interchangeably because mu is easier to understand in analog of quantum mechanics. But at the end of the day, like practical calculations, we only care about alpha. You can think of this alpha as being like kind of the finite part of mu that ends up being the symplectic partner to A.
Maybe another way to ask one question. So this mu tilde with minus sign, are you looking at the time derivatives for in all directions that are inwards or outwards?
That are
Along the horizon.
along the horizon.
horizon.
Along the horizon.
Not
That's
up.
right. That's correct.
Okay.
That's right. Because in the phase space that we have set up, there is no evolution out of the horizon.
Right,
Like we
right.
start with just a causal diamond and that's it.
Right.
Mhm. Yeah. Thank you. Okay, so why do we want to write down the symplectic form? The reason we do is because it allows us to derive the Poisson brackets. And so the Poisson brackets tells us how A and mu or A and alpha once we canonically quantize what their commutators are. And here we see that their bracket is just minus A pi g Newton. And importantly, this is an algebra that is defined only at the corner. Oftentimes when you use covariant phase space formalism, you get an algebra that is defined on a codimension 1 slice. This is indeed what happens in quantum mechanics. You define the field and its a time derivative on a Cauchy slice. That's codimension 1. Here, things end up actually localizing onto a codimension 2 surface. And this is the reason why people sometimes call these edge modes, because it's like the edge of the codimension 1 slice. But there is another place where we have seen this before. This is indeed exactly what happens when you compute the symplectic form associated to the leading soft graviton and its symplectic partner, which is the supertranslation Goldstone mode. They are both defined on the celestial sphere, and the celestial sphere is a codimension 2 surface. So this is where we started thinking there is probably an analog that we can relate the asymptotic analysis to this finite causal diamond analysis. And we actually make it very precise for abelian gauge theories, the relationship between edge modes and soft modes in this paper with Prahara Mitra, Alex Ramakrishnan, and Catherine Ziris back in 24. We don't have that precise connection for gravity. So for the rest of the talk, I will restrict myself to just the phase space. And we're going to relate the phase spaces between these two setups. So that finishes my the part of the talk where it just focused on the causal diamond itself. Now, the question we want to ask is, can we interpret these area fluctuations of large causal diamond as corresponding to a memory effect that's arising from the infrared sector of asymptotically flat gravity? And the reason why we're going to do this is because it's oftentimes much easier for us to work with the asymptotically flat gravity. There we know the soft graviton theorem, everything is under very good control due to progress that have been made in the last 10, 15 years. And intuitively, it should apply because whenever we say asymptotically flat spacetime, we take a large R limit. But R is dimensionful. So what do we really mean when we say we take a large R limit? It means that we're taking a limit where the size of our system is much bigger than any other interaction length scales that we have in the problem. Now, for a vacuum spacetime, there is only one other length scale that we have in the problem, and it's a Planck length. It's L Planck. So as soon as our causal diamond, the intuition goes is as soon as the causal diamond, the size of it is much larger than the Planck length, then we should be able to apply our analysis. And so what I will try to do in the next several slides is try to make that connection precise. So as I said, so far everything that we have been studying is a Minkowski diamond whose area is fluctuating radially. And what we want to do is we want to map this to an asymptotically flat spacetime where the fluctuations of the area in asymptotically flat spacetime is captured by the soft graviton mode N in its symplectic partner C. And what we want to do is come up with a map between the two phase spaces that preserves the bracket. So here, this is the spacetime diagram I showed you on the previous slide, or previous several slides. And this is the Penrose diagram associated to asymptotically flat gravity. So these blue wiggles are just supposed to explain that, like, this is, asymptotically flat. So in the bulk, we don't care what it's doing. As long as on the boundary, it becomes Minkowski spacetime. And Scri plus minus, this is the past boundary of Scri plus. And this is where the celestial sphere lives. And on the celestial sphere, we have the graviton mode N and the ghost mode C. So we see again, the degrees of freedom here lives on a codimension 2 slice, not a codimension slice. And for purposes, because we live in 4-dimensional space-time, we're just gonna focus on 4D for the rest of the talk. Okay, the first thing that we want to do in mapping between the asymptotically flat spacetime and our finite causal diamond is we want to look at length fluctuations rather than total length. The reason for this is just because when we go to asymptotically flat spacetime, the L length itself diverges, but it's still perfectly fine to talk about length fluctuations. So the way that we're going to do this is we're just going to define the mean length L naught to be the integral over the probability distribution of all possible causal diamond in the phase space. So this is just a standard way of computing the mean associated with L given a probability distribution. And L naught is a phase space constant, so we can isolate the fluctuating radial mode by just subtracting off L naught. So epsilon is going to be something that is reasonable to understand from the perspective of asymptotically flat spacetimes. And epsilon and L, they have exactly the same algebra because L naught is a constant, so it just disappears. Every time you put it inside a Poisson bracket, it just disappears. Okay, so now recall that the Poisson bracket that we have derived previously is given by this. And we can just replace A with 4 pi L squared and then write L as L naught plus epsilon. And at the end of the day, when all the dust have settled, the bracket we get between mu and epsilon is just minus G over L. And this inverse L on the right-hand side, this is an interesting feature, and we will see that it will contribute to the fact that the mapping between the two phase spaces is not going to be a linear. So far, I've said a lot about asymptotically flat spacetimes, and I hope that intuitively you guys know what it means. But let's now be a little bit more precise because we're serious physicists. What do we mean by asymptotically flat metrics? So this was first studied in 1962 by Bondi, Vanderberg, Messner, and Sachs. And the class of spacetime metrics that we have in mind is given as follows. So let's first just focus on the first line of this equation. So U is just the retarded null time is t minus r. R is a radial coordinate. And z and z bar are just the complex coordinates on the celestial sphere. And gamma z bar is the round metric on this sphere. This first line is nothing more than just Minkowski metric. So this first line is just minus dt squared plus dx squared plus dy squared plus dz squared. That's it, written in these particular coordinate choices. Now, what makes this non-Minkowski but asymptotically flat is the presence of the second line. So MB, this is the bonding mass aspect, and this measures local energy fluctuations. And notice that this term is completely subdominated by the minus du squared when we take r goes to infinity. CZZ, this is oftentimes called the shear tensor, and it corresponds to transverse fluctuations. And you might be worried that there's a r multiplying CZZ. So if we take a large r limit, it seems that it would diverge. But of course, that is spurious because this piece is completely subdominant to the r squared gamma ZZ bar that's showing up in Minkowski metric. So this term is again completely subdominated by the main part of the transverse metric in Minkowski spacetime. And so again, this is something that we don't need to worry about once we take the infinite r limit. And there's also another piece of data that we oftentimes see in these metrics. It's called the News tensor, and it's just a U derivative of CZZ, and it measures gravitational radiation. The dot dot dots, these are all completely determined order by imposing the vacuum Einstein equations. And the first, to lead in order, when you impose the vacuum Einstein's equations, you actually get a constraint equation between the time evolution of the body mass aspect and the News tensor. So you can see that the News tensor completely governs how the evolution of the body mass aspect, how it behaves. To answer Nima, one of your earlier questions, it is precisely this equation that tells you that if you have some body mass aspect, it's changing. You can still stay completely within the realm of vacuum solutions of Einstein gravity, and nevertheless, you will start seeing shock shockwave-like behavior, as long as the body mass aspect has a step function sort of behavior. Now, using the covariant phase space formalism, again, you can determine what are the degrees of freedom associated to these asymptotically flat spacetimes. As this was worked out first by Ashtekar and Struve back in '81. And what you see is that the symplectic partners are CZZ and NZZ. So again, to draw analogy with quantum mechanics again, CZZ, if you associate that with the position, NZZ is roughly speaking the time derivative of CZZ, that is the momentum. But this is a symplectic form for not just the soft degrees of freedom. What we are interested in is we only care about the soft degrees of freedom. And so one way to extract this is actually choosing a particular choice of shear profile, which we call the memory shear. So it was shown that if you just restrict yourself to shears of this form by Strominger and Zhiboyev back in 2014, and we also use this very heavily in the paper by Leclerc and Dirac, then you isolate to the leading soft sector of your phase space. So here theta is just a step function. So all we're doing is CZZ, we're taking it to have an initial value of -2 dz squared c. C is what we call the Goldstone mode. And for after u is bigger than us, you then get an extra contribution of dz squared n. So what we're doing is we're changing CZZ from -2 dz squared c to dz squared n -2 dz squared c. And n is a soft graviton mode. And this is precisely, the step function is precisely capturing the gravitational memory effect. This is the shift that you see in the metric when you have a burst of gravitational radiation. It's changing the separation between the two objects from one distance to another distance. Okay, so now you just stick that into the symplectic form and you just compute. And what you get is that C and N are the symplectic partners to each other. And notice that previously, the symplectic form, it's a codimension 1 integral. I'm integrating over time. But because NZZ, I take a u derivative of this is a delta function, I can integrate over this u delta function. So at the end of the day, once I look at the soft sector, I have a codimension 2 integral now. So this is how we start seeing this equivalence between the finite causal diamonds and the soft sector of asymptotically by gravity. And of course, here so far we haven't assumed spherical symmetry. So what we want to do is we want to perform an angle average. And after we do that and invert the symplectic form, what we get is that the bracket between C and N, both angle average, is -2g. And this is starting to look very similar to the bracket that we had for finite causal diamonds.
So just
Yeah.
move with loss and notation. So this integral over S2, is it out at infinity? Or
Yes,
Okay, so
it's at the corner.
right. Mu of S was so U of S. U of S, sorry, right?
U of S.
U was this like direction in the along the null infinity.
That's correct.
Yeah, I see. So that's where the shockwave is coming.
That's right. Okay, so how are we going to relate the two phase spaces? So first thing we're going to do is we want to look at how the area fluctuation is being parameterized in the two phase spaces. There's an equation that was written down for us very conveniently. It first showed up in a paper by Kopets, Leclerc, and Strominger back in 2016. It's very possible it showed up earlier in literature, but this is the first place where I saw it. The induced radial coordinate on a null hypersurface, it just obeys this following differential equation. So what we want to do is we want to geometrically relate the causal diamond mode epsilon, which captures the fluctuations of the area of a finite causal diamond, to the soft graviton mode N, which also, it turns out, measures the rate at which area fluctuations change at the corner. So the way to do this is very simple. We just look at the two different spacetimes, we stick it into the differential equation that I showed on the previous slide, and then we just compute. So for a causal diamond and Minkowski spacetime, we can just set MV is equal to 0 because Minkowski spacetime body mass aspect is equal to 0. And you can very quickly see that the rate at which the area fluctuations change is just controlled by the length fluctuations, which is captured by epsilon. So that makes sense. And it turns out that it takes a little bit more work, but you can compute that the rate in which the area fluctuations of asymptotically flat gravity changes as a function of the retarded time is controlled by the body mass aspect. So if we want to maximize the corner, which is where the phase spaces live, then the identity that we get is that we should identify the length fluctuations for the finite causal diamond with the body mass aspect defined as a corner.
Is the epsilon is length?
Epsilon
right?
is
L
length
minus
fluctuation.
L naught.
Yes.
But body mass is mass.
Yeah, so this is body mass aspect has units of length.
Oh, it's like so inverse. mass.
It's like mass divided by like L Planck or something like sorry, divided by G Newton or something like that. Because the body mass aspect, it's just unfortunate term not. See, it shows up in
Oh,
a metric like this.
You
Yeah,
mentioned like.
yeah, yeah,
Sorry, yeah.
yeah. I mean, I wasn't there in 62, so I can't. Yeah, I just go along with what people are.
Yeah.
But yeah, it is a common confusion. Okay, great. So we have identification between length fluctuations and the body mass, excuse me, in the body mass aspect. But we ultimately want to identify the soft graviton mode with the length fluctuation. And we can do that because we have a constraint equation that relates the body mass aspect, in fact, the rate of change of the body mass aspect in the soft graviton mode. And that is given by the constraint equation. So at the end of the day, we are able to get a geometric identification between the 2 degrees of freedom in the phase spaces. Essentially, we should think about the the soft graviton mode as corresponding to the length fluctuations. Once we have that, we can just utilize the fact that we know the brackets between N and C, as well as the bracket between epsilon and alpha, to make the identification that C is proportional not to alpha, but rather to alpha times L. And it is this part that with the L in the denominator shows up, and we see that the mapping between the Goldstone mode is not to just a single operator, but rather it's up to a product of operators. And importantly, we see that Goldstone mode is related to the IR scale L here. Okay, so now that we have identified an isomorphism that preserves the symplectic bracket between the 2 phase spaces, what we're going to do now is we're going to use an asymptotic analysis to construct a vacuum state for a large causal diamond. And in particular, we're going to utilize what is called a soft effective action, and to reproduce this equality. So let me explain quickly what I mean when I say that we're going to use the soft effective action to construct the density matrix. So people in 2021, Bar Mitra and Dan Kapets, they were curious as to if you do a path integral calculation, how, like, suppose I want to compute a correlation function of soft operators. Can I do a path integral calculation that produces exactly the correlation functions that we know these soft operators have to obey in scattering amplitudes? And that is what they call the soft effective action. So let me just say in a bit more mundane terms. So suppose I want to compute a correlation function of any operators in Einstein-Hilbert gravity. What do I do is I insert these operators in the path integral, and the path integral should be weighted by e to the minus s Einstein-Hilbert. Now, suppose I don't care about any of the energetic modes. I just want to look at what happens in the soft sector. So what you typically do is you do a mode decomposition of the Einstein-Hilbert action, and then you integrate out all the energetic modes. And whatever that's left in the path integral, that is a soft path integral. And there's going to be a measure factor that's associated with that as well. That is e to the minus s effective. Now, doing that procedure is very, very challenging, but what Kapets and Mitra were able to cleverly do is by just imposing consistency with known results in the scattering amplitudes in the infrared, they were able to deduce what the S effective is. So we know how to compute the second line. But there's another way of computing correlation functions. It's by taking a trace over a Hilbert space of the operators multiplied by the density matrix, rho s. The question that we want to answer is, does there exist such a rho s, given the fact that reproduces this path integral calculation? And the answer, it turns out, is yes.
Sorry, I'm only confused. How do we know that the soft modes will form an algebra? Because you don't have a gap or anything to say.
Right.
In an RG sense, you're gonna perform RG, everything's gonna get integrated out. Yeah.
So you can do a covariant phase-space analysis, and it turns out that the soft sector completely decouples from the hard sector. And so the soft sector themselves, these are the C's and N's. Once you promote them to operators, they form an algebra amongst themselves. That does have to be checked.
Yeah.
Um,
And physically, it's because you have arbitrary low energy mode, right? It's not like the system is gapped.
yeah, that's right. So the way that you should really think about these is not that these are sort of low energy creation or annihilation operators. You should really think of this as corresponding to a set of boundary conditions that you're allowing your theory to have. Different boundary conditions correspond to different choices on this vacuum moduli space. And what C and N do is that they move you around in this vacuum manifold. So in fact, now what we're going to, thank you for the question, because we're going to get exactly to the point. We're going to construct the sort of the Hilbert space that lives in the soft sector. So the first thing we do is we canonically quantize so that we elevate the Poisson brackets to quantum commutators by multiplying an I. And the result is as follows. So here I just wrote CZZ and NZZ so that I don't need to keep on writing these transverse derivatives. Just apologies, kappa is 32 pi g Newton. This is not the surface gravity kappa that I showed on the earlier slides. Now, the C and N, they do not commute with each other, but importantly, C, they do commute with each other, which means that you can choose a basis that simultaneously diagonalizes the C operator, and that's going to be the basis that we work with. So these are called the C eigenstates. You can think of each C as corresponding to essentially a cloud of soft gravitons. And if you think of N as creating a soft graviton, then every time you act on one of these C eigenstates of N, what it's doing is shifting you from one vacuum state to a different vacuum state because you're effectively adding like a soft graviton into the cloud. And so the C eigenstates, they are just C have just act via multiplication. And these C's, they are delta function normalizable. So these are not truly normalizable states in the strict sense. But they are useful to consider, just like plane waves are oftentimes very useful to consider in quantum mechanics. Okay, so what is soft effective action? So let me just first write down what it is. So the soft effective action, so kappa squared is again 32 pi g Newton. This integral is just the integral over the celestial sphere. And alpha is the IR divergence that you guys may have encountered in four-dimensional gravity. So it's a log of two energy scales. Lambda is the energy scale that demarcates soft gravitons from hard gravitons, and mu is the IR cutoff that you ultimately want to send to be zero. So in four dimensions, this is what alpha equals, and it diverges. And you see, though, that the soft effective action is quite a simple action. It's a quadratic action. And this is the reason why we wanted to work in the asymptotic limit, because here we don't need to worry about these various interaction terms. This is another way of seeing why the Weinberg-Soft theorem is so universal. All these messy interactions, they just die off. Now, the way that Kappa and Mitra were able to beautifully derive this equation is because they just imposed two conditions. So they were able to get the n squared condition by looking at the way amplitudes factorize in the infrared. And they were able to get the Cn term by just requiring that if you insert a soft graviton into the path integral, that you reproduce a Weinberg-Soft factor. So it's quite amazing that you're able to fully fix the form of the soft effective action by just imposing these two simple conditions. We actually want to process this action a little bit more because at the end of the day, we want to write a density matrix in terms of the C eigenstates. So what we want to do is we want to integrate out n. So you just vary the soft effective action and you require that it vanishes. And that gives the equation of motion for n, which is as follows. You substitute this back into the soft effective action, and what we get is the final form that we are going to be using, which is that it's just a quadratic in C. This is nothing more than a Gaussian. Excuse me. Okay, but now we're basically done because I claim that the following density matrix actually does the job. It's just taking the exponential of the soft effective action where the C's are now not treated as fields, but as operators. And you might be worried about this log C inner product with C, because this is actually divergence. I'm happy to discuss this afterwards. The short answer is this is a very innocuous divergence. This shows up because the states that we're using are not normalizable states or delta function normalizable, but this is exactly the sort of divergence that shows up in a particle in a free potential in quantum mechanics. So I am happy to talk about more about this afterwards, but you can also think of this as just a normalization factor to ensure that your density matrix is appropriately normalized. Now, why does this work? Because it's really a one-line computation. So suppose we want to compute the correlation function between O1 through On. So the way that we do this is we take trace of rho s times this, and we just substitute this into the sum over all the operator sandwiched by all the basis states, which is given as follows. But now we know that rho s is written as just C operator, so we can just pull it out. And similarly, every single one of these operators, it's a soft operator. So it's either a function of C or it's a function of N, which we can rewrite using the equation of motion in terms of C. So at the end of the day, the only thing that survives is just C inner product of C, which cancels out this e to the minus log C inner product of C. And so what we get is this answer. And this is, of course, is precisely the path integral representation of that we have been looking for. So this fits the bill. Now, once we have this density matrix, we can now compute what the vacuum modular Hamiltonian is. And this is just minus trace, this is just minus log of the density matrix, and it's given as follows. And now that we have a modular Hamiltonian, we can now compute the mean and the variance of it. And the way that we're going to do this is to decompose C into spherical harmonics. Now, I just want to pause quickly to mention that if we had a unique ground state, then we would never have been able to write down a non-trivial vacuum modular Hamiltonian, because there's just be a pure state for our density matrix. So that corresponds, once I take the log of a pure state, that just gives me 0. So the fact that we're getting a non-trivial modular Hamiltonian already presupposes the fact that we are living in some non-trivial vacuum that does not have just a unique ground state. And this is something that is very difficult to capture using Feynman diagrams. But it's something that I think is very important to understand, to really understand, because this has to do with the nature of infrared divergences and so on. Okay, so back to this computing the moments of this modular Hamiltonian. Now, suppose I want to, okay, so in order to decompose this into spherical harmonics, I actually need to impose a cutoff, which I call Lmax. This is the UV cutoff. And we have a geometric interpretation for what that cutoff is. Because suppose I think about this as a density matrix associated to some very large causal diamond with area A. I need to regularize it by both imposing the size of the causal diamond, which is an IR cutoff, and I need to basically discretize the sphere, because I basically want to say that within some small length scale governed by epsilon, it no longer makes sense to talk about separations of that short distance. Now, if you hand me a function on this discretized sphere, how many degrees of freedom are needed to describe this function? Well, the number of degrees of freedom is just a over epsilon squared, because I need to specify the value of that function for every plaquette of size epsilon squared. But there's another way of describing the number of degrees of freedom to describe a function. It's just given by the number of spherical harmonics that you have. So, and that is given by Lmax plus 1 quantity squared. So this gives a geometric meaning for what Lmax is. It's just, Lmax is just a square root of A over epsilon squared, where epsilon is a UV cutoff and A is the IR cutoff. And this -1 is not important because the first number is very big. With this, we can now compute both the mean and the variance of the modular Hamiltonian. And the mean, as you can see, this is the entanglement entropy, and it does have this log C divergence here. But the entanglement entropy is not unobservable, so that's why we're not super worried about this divergence. What is unobservable is the variance of the modular Hamiltonian. That's a fluctuation of the entanglement entropy. And of course, so if we want to compute the variance, we should hope that any sort of spurious divergence should go away. And indeed, that is what happens. You can see when you compute the variance of the modular Hamiltonian, this log C term just cancels. And we see that the variance of the modular Hamiltonian is proportional to A over epsilon squared. Now we can relate this to area fluctuations, because if we assume that epsilon is of order of Planck length, and the entanglement entropy is A on 4G, then for this particular vacuum state, what we get is that the variance of the area is precisely proportional to G Newton, which is a UV scale times area, which is an IR scale. And this is another way of saying what sometimes people call UV-IR mixing, is that these area fluctuations, which is an observable, do depend on both the UV and the IR scale. And also it confirms of a different paper that we wrote with Luca Ciambelli and Catherine Zurich independently. The last thing that I want to remark is that it's a cute observation that we made, which is that in 4 dimensions, if you just, let me just write down what the vacuum density matrix is, it is given by exponential of this quantity. Now, alpha is the IR divergence. So we should really be taking alpha goes to infinity. And once you take alpha goes to infinity, we see that the density matrix effectively becomes the identity matrix. This is a way of seeing that the vacuum state in asymptotically flat gravity, or that of a very large causal diamond, is maximally mixed. And it resonates with the statements that Jacobson and Silverstein and many others have made about the vacuum state in de Sitter spacetime being maximally mixed. However, what's nice about our analysis is that whereas previous analysis, they required thermodynamic assumptions of gravity, here we really, the only thing we imposed is consistency with the infrared behavior of scattering amplitudes. And we get in a very controlled fashion, essentially, that the same maximally entanglement property of the vacuum holds not just in de Sitter spacetime, but also in asymptotically flat spacetimes as well. Okay, so now let me summarize. So what did we do? We began by constructing the vacuum state of a finite causal diamond in the spherically symmetric limit, and then we demonstrated its relation to angle average soft and Goldstone modes. Once we did that, we were able then to utilize the connection between asymptotic analysis and the causal diamonds to construct a vacuum density for density matrix for a large but finite celestial sphere. And in order to compute moments, we discretized it. And we find that the size of the area fluctuations, the variance in particular, depends on the product of a UV scale and IR scale. Now, this is certainly not the end. I began by motivating the fact that we want to compute the quantum memory effect, whereas everything that I've said so far is not able to make connections with the actual observables. We learned a lot about the connection between the soft modes, edge modes, and the vacuum density matrix, but everything that I have said so far is still at present completely formal. What we need to do is actually compute a quantity that experimentalists care about, and that is the power spectral density of these length fluctuations. I think it is very important for us to do this because ultimately the experimental colleagues are making, they're working very hard to come up with building this experiment. So as theorists, we hope to make their lives a little bit easier by telling them hopefully what to look for at particular energy bands. So with that, thank you very much. And yeah, I learned recently that there's this notion that gravity is magical. So I just decided to put this comic where it's a magical world. So let's go exploring. Sorry.
Thank you so much. Are there any more questions for Temple?
You mind saying a little bit more about the UV-IR mixing? Is it surprising, unsurprising?
Yeah, so it depends on who you talk to. So I would claim that this answer is not surprising because the fact that the area fluctuations also depend on the size of the area, like, it's something that like just makes a lot of intuitive sense, right? Like if I have some very large sphere, I change the radius a little bit. Of course, it's going to depend also on the initial size of the radius. So in that regard, like, this answer is almost trivial. But on the other hand, this is going back to Nima's point, like, how do I think about this in terms of a gravitonic exchange? Like, I don't know how to recover the IR scale. If you hand me a bunch of Feynman diagrams and say like, how do I write down the Feynman diagrams that correspond to area fluctuations? Yeah, these are at the end of the day graviton fluctuations. How do I see that? I don't have a good answer to that. So it really depends on your viewpoint. For some part of the community, perhaps this is obvious. For another part of the community, this is absolutely, this cannot, like, how do you even get a IR scale out of this? Like, everything has to depend on the gravitational coupling constant, right? Like on square root G Newton. So yeah, so that's what I mean by UVR mixing. Like, it's not clear whether or not one would expect this. Like, it really depends on your point of view and the approach that you take. So this is why I said it would be very instructive to try to understand this from a gravitonics change, if we can get this result. Because, and understand, it's very difficult because Feynman diagrams are not set up to compute these sort of vacuum transitions. Feynman diagrams from the very beginning assume that you have a unique Lorentz invariant vacuum. This is why doing like deforming T goes to T minus I epsilon, and then you have this ET minus, the fact that it picks out a vacuum for you, like that is already built into the assumption. The fact that we don't have a unique vacuum, and that's a wrong assumption, shows up as IR divergences. So one would really have to understand like what part of the IR divergences to keep and what to throw out. That I think that has to go into understanding this from gravitonics.
Any other questions? If not, let's thank Temple again for the wonderful talk. Thank you so much.